Hi everyone, welcome on this third video from the series on implicit regularization, Benign interpolation, and Benign overparametrisation. So today we will focus on the mathematical aspect of Benign interpolation. So we will do a rigorous mathematical analysis of what we have discussed in the previous video. So maybe before we move on this mathematical analysis, I will do a short recap of what we have seen so far. So we have been considering a Gaussian linear regression with a Gaussian noise. So when you have a Gaussian linear regression, you know that maximum likelihood estimation amounts to do some least square minimization. So we are interested in the setting where we have interpolation. So this is a setting where the input dimension P is larger than n, and where the rank of X is n, so it means that X is full rank. So in this setting, you know that you have at least one solution of the equation y equal to x beta. So since you have one such solution, it means that any minimizer of your least square is actually a solution to this equation. So this corresponds to an interpolating solution. So what we have been considering is a specific solution, which is a solution which is obtained when we apply gradient descent on the least square criterion. And we will start from 0. So what we have seen in the first video is that in this case, we end up with an estimator which is given by the product of the Moore-Penrose pseudo-inverse of x times y. And there is something special with this solution, which is that in our interpolation regime, this corresponds to the interpolating solution which has the minimal norm. So this is something that interpolates because we know that minimizing the least squares must be, so a minimizer must be an interpolating solution, but this is not any solution, this is the one which has the smallest norm. So what we have seen is that gradient descent has some implicit regularization effect, and we want to understand what is the statistical effect of this implicit regularization. So what we have done in the second video is to try to discuss a little bit this effect with some non-rigorous computation. So let us have a look to the result of the second video. So first of all, what we have done is to analyze the average prediction error conditionally on the design. So this is this quantity here, where we consider the prediction. So for a new point x, I will predict the output by beta hat scalar x, and I want to compare this to the optimal predictor, which is beta star scalar x. So I take the difference of the two, I put it to the square, and I will take the average over the noise, epsilon, that we have in the learning dataset, and on the design of the point x. So we assume that x follows a Gaussian distribution with covariance sigma, so exactly as the learning data point, so the learning xi, and epsilon is Gaussian with a variance sigma. And we work conditionally on the design x. Okay, so we work conditionally on the learning point xi. So what we have seen in this case is that this average prediction error is a sum of two terms. One term, which is the bias term, which is given here, and another term, which is a variance term, that is given here. So what you have in mind is that usually in high dimension, we have issues with the variance. So we mainly focus on this variance term, Vx, and we try to understand it. So if you want to understand it, what you see is that this is something quite simple. So you have the covariance sigma of the x, and you have this matrix here, which is the Moore-Penrose pseudo-inverse of x transpose x, and we take the Frobenius scalar product between the two. So essentially, we have to understand how this matrix behave. And for this, we need to understand how x transpose x behave. So we have done some non-rigorous computation in two specific cases. One which is the isotropic case, where sigma is the identity, and the other one is the spike model that I will describe later. So first, let us start with the isotropic input. So what we have in this case is that when P is large in front of n, if you look at X transpose X, it essentially looks like P times the projector on the range of X transpose. So essentially all the eigenvalues, non-zero eigenvalues, are the same, they are equal to P, and we have something which lives in the range of X transpose. So now, if you want to look at the Moore-Penrose pseudo-inverse, you know that you will just have to invert the eigenvalues. So the Moore-Penrose pseudo-inverse of X transpose X will be 1 over P times the projector on the range of X transpose. And just by using this result, we obtain that the variance term, in this case, so since sigma is the identity in my variance term, I will have simply the trace of this matrix, and the trace of this matrix will be equal to n over p, just because this is a projector on the space of dimension n, and you have the 1 over p here. So we have this very non-intuitive results, which tells us that the variance behave essentially like sigma 2 n over p. So this is something which goes to 0 when p goes to infinity. So we are used to have something like the dimension over n, and here we have something which is the opposite. We have n over the dimension. And as we have discussed, this is essentially due to the fact that when you take a new x, it is almost not correlated with the learning data point x1, xn. And this is why we have a very small variance, and this very small variance is nice, but at the same time, when we compute the bias, we see that we have a bias which is very large. So it is essentially equal to the square norm of beta star up to some small factor 1 minus n over p. So if p is very large compared to n, you essentially have 1 here. So what we see is that we have a bias term which essentially corresponds to the bias when you predict with 0. So at the end, we see that in the risk, we have almost no variance, but we have a large bias. So this is quite counterintuitive because we are in a very high dimensional setting where we interpolate, and we are used to believe that in this case, we have a small bias on the large variance. Then we have discussed another case, which is anisotropic, which corresponds to a spike model, where on a small space, you have the identity, and otherwise, you have something which scales with some rho, which is very small. Okay, and here the space k is very small compared to n, so it's a space which has a small dimension compared to n, and n is small compared to p. Okay, so the sample size is small compared to the whole dimension of the space. And what we have discussed is that in this case, essentially, if you look at X transpose X, it will be essentially equal to n times the identity. So for the low dimensional part, we essentially recover here this matrix. But for the high dimensional part, what we will have is something which will be like rho, so this factor here, which is small, times p, which is the input dimension, times this matrix, which is a projection of rank n minus k, and that will be a random projection of rank n minus k. And by doing this non-rigorous computation, we end up with the following guess, which was that the variance can be seen as being the sum of two terms. The first term, which corresponds to the classical variance when you do some linear regression in low dimension. So it is sigma 2 times the dimension divided by n. So this is really standard result if you do linear regression in low dimension. So this corresponds to this part. And for the high dimensional part, what we have is that we have a variance which will be, so we have sigma 2, of course, times n over p. So we have again this n over p term that will be small because we have p that will be very large compared to n. So this term tends to be small in very high dimension. So yeah, what you can see is that this setting, where you have a low dimensional part in a very high dimensional space, what you will have is a variance which is small for two different reasons. Here it is small because k is small compared to n. So this corresponds to classical low dimensional estimation. And this part is small due to the high dimension of the input. And again, this will be the same. If you take the input in this space, or which corresponds to this space, it will be almost not correlated. The new input will be almost not correlated with the learning input. So this is why you have a variance which is very small. So all these are non-rigorous computation, and what we will do today is rigorous mathematical analysis. So this lecture will be somewhat more technical than the previous ones, and maybe I suggest, if you have not done it, to first take a good cup of coffee. So let us start our mathematical analysis. So I'll just do a short summary of what I have as a recap. So we have some learning data points. Xi follows the Gaussian distribution n0 sigma, and now we consider any sigma. And what we observe is yi, which is a scalar product between xi and some unknown beta star, and which is corrupted by a noise which is iid, Gaussian, with variance sigma 2. We consider the least square solution selected by gradient descent started from 0. So we consider the estimator given by x plus y, where x plus is the Moore-Penrose pseudo-inverse of x. And we compute the average prediction risk, which is the sum of this variance term here and this variance term. And we will mainly focus on the variance term. So I have said before, in order to understand this variance term, we need to understand this matrix. So our first goal will be to understand what is this matrix, how does it behave. So it is not very easy to look at this matrix. Why? Because if you look at x transpose x, so this is a matrix which is p by p. But what is the rank of this metric? The rank of this metric is equal to n. So it means that you have a matrix which is p by p, but which have a very small rank. So it is not very easy to describe this. And instead, we will focus on the matrix x transpose. So why do we focus on x transpose? Well, there are two reasons for this. The first reason is that if you look at the non-zero eigenvalues of x transpose, so what I denote by spec star, it just means that I look at the spectrum, but with only the non-zero eigenvalue. So the non-zero eigenvalue of x transpose are exactly the same than the non-zero eigenvalue of x transpose x, even with the same multiplicity, right? But this matrix will be easier to analyze because this is a n by n matrix which has full rank. So it will be easier to analyze it. So when I say that it is full rank, it is in the high dimensional setting where p is larger than. So let us look at this matrix. So I need to introduce some notation for the following. So I will denote sigma in this way. So I will assume that sigma is diagonal. So assuming that sigma is diagonal is not really an assumption. Why? Because you know that you can diagonalize sigma in some orthonormal basis. And since gradient descent is invariant by the change of basis, orthogonal basis, you can always assume that you are in the coordinate of this orthogonal basis. So you can always assume that sigma is diagonal. It will not change anything. And it will be much easier for the notation. And what I will assume also is that I have lambda 1, lambda p here, so which corresponds to the eigenvalue, and that rank in decreasing order. All right. So here I have some lambda which are large, and here I have some lambda which are small. And I will introduce a number, kappa star, that will be very important, that will essentially tells us what is the important dimension of the problem. The kappa star is defined as follows. It is defined as the smallest k for which the eigenvalue k plus 1 is smaller than some constant rho. So here the constant will be 1 over 142. So there is nothing special with this number. It is just a small numerical constant. So we look at the smallest k for which the eigenvalue lambda k plus 1 is smaller than this constant over n times the sum of all the remaining eigenvalues. So all the eigenvalues that are larger than this one. And we see that this kappa star will play an important role, and essentially we'll have data which will be for j smaller than kappa star, and here we'll have some low dimensional effect, and we'll have the portion of the space where j will be larger than kappa star, and here we'll have a high dimensional effect. So we will split in our x, we will split our data. Okay, so here we will have kappa star, here we have the remaining terms. So we will split our x into two parts. The first part denoted by x small, which corresponds to the part where the lambda j are large, and second part x large, which correspond to the part where you have small eigenvalues. And the same, I will denote sigma by the part with large eigenvalue and the part with small eigenvalue. And I will use this color green for the low dimensional part with high signal and red for the high dimensional part with small signal. So the signal refers to the amplitude of the eigenvalues. All right, so what we want is to understand this matrix in order to understand this matrix. So what we'll do is to look at what's going on for this part and for this part. And why so? Because what is nice with x transpose is that you just have this decomposition into the green and the red part. So you have, when you look at x transpose, you have the sum of the low dimensional part plus the high dimensional part. Okay, so these two parts are disentangled, so we can easily analyze them. So the first result is as follows. So when k star, so k star is this important dimension, which corresponds to the low rank dimension. If k star is small compared to n over 600, so again 600 has nothing special, it is just a numerical constant, then with large probability what we will have is that, so if I look at x transpose x but only for the low dimensional part, and I rescale by sigma minus 1/9 restricted to the low dimensional part, this essentially looks like n times the identity on k star. So here we have something of dimension k star by k star. Here also, okay, so this is k star by k star. And you have that this matrix essentially looks like n times k star. So of course this is not exactly true, but you have some control on the operator now. So this is something that typically happens if I were just doing some linear regression with just this part, okay, just this covariance, then this is what we will have. So this is nothing special in this case. What is special is for this high dimensional part, so the red part here. Here what we can see is that if you look at the eigenvalues, non-zero eigenvalues of this part, they are almost all equal to the sum of the remaining eigenvalues lambda j. So for j larger than k star. So of course this is not exactly equal, you have something here, but this will be of the same order of magnitude. Since here you have a 3/3, you know that this will be larger than 1/4 of this, and this will be smaller than at least twice this quantity. Okay, so it is of the same order of magnitude. So just a recap of what I have already said. So if you look at the empirical covariance for the low dimensional part, it is close to the true empirical covariance. But if you look at the low signal part, which is in high dimension, it has a flat spectrum, which is around this quantity. So let us prove this result. That will be really the core of the analysis of our gradient descent least square. So to prove this lemma, we will need to prove first two lemmas, which are more general than what we want to prove. So the first lemma will be a simple version of Hansen-Wright inequality. So Hansen-Wright inequality is a concentration inequality for quadratic forms of Gaussian or sub-Gaussian random variable. So here I will look at very simple quadratic form, that will be quadratic form of this form. So if you take epsilon, so x epsilon j, you assume that they are IID and 0, 1. I take some numbers, alpha j. What you will obtain is that, so if you take the expectation of this quantity, of course it is, because this expectation is linear, so this is the sum over alpha j of the expectation of the epsilon j square, and this is equal to 1. So this is simply equal to the sum over j of the alpha j, okay? That I denote here shortly by alpha transpose 1. So this is just the sum over j of the alpha j. So this is the expectation of this quantity, and what we will prove is that we can upper bound the difference between the two, so between this quantity and its expectation, by this term. So what we will show is that there exists a random variable which follows a distribution with exponential 1 parameter, such that you have that this fluctuation here is smaller than the maximum of these two quantities. So the first quantity is the square root of 8 times the square of the norm of alpha times xi, and the second term is 8 times the subnorm of alpha times xi. Okay, so this is simply the largest value in absolute value of alpha j. So it will be convenient to use a bound which is not as good as this one, which will be the second bound. So what we will use in the following is that this in turn can be upper bound by 1 over 4 the L1 norm of alpha. So the L1 norm of alpha is just the sum of the absolute value plus 8 times, so the subnorm of alpha times xi. So how do we prove this? The proof is very simple, and it is based on the Chernoff method. So when we want to use the Chernoff method, so what do? We compare, so we start from here, we compare the probability with this quantity here, which is the characteristic function of this quantity. So this is exponential minus, okay, sorry. So this here is the expectation of exponential s times sum over j of alpha j epsilon j square minus 1. Okay, so I just use Chernoff inequality, and in my Chernoff inequality, since I have exponential of a sum of independent random variable, this exponential of sum of random variable will become the product of the expectation. Okay, so the expectation of the exponential of the sum of independent variable is the product of the expectation of the exponential of the variable. So I end up with this formula just by using Chernoff. So now I need to evaluate this quantity, and to evaluate this quantity, so I remind you that here epsilon j is a standard Gaussian. So what I will do is to compute the Laplace transform for my standard Gaussian to the square that I will recenter. So this is a very simple computation that you can do. and you find that the expectation for this exponential of minus a standard Gaussian variable to the square minus 1 is given by this exponential minus lambda over 1 minus 2 lambda, and you take the square root. So this is not very convenient, but we will use the following inequality. So if you have x in absolute value which is smaller than 1/2, then you can upper bound minus log of 1 minus x by x plus x squared. So here I can upper bound this term by something like this. So this is equal to exponential minus log 1 minus 2 lambda, and there is a 1/2 in front of it. Okay, so I can upper bound this by using the above bound, so it will be smaller than exponential x to the 2. So it is not x, this is 2 lambda to the 2 plus 2 lambda square to the 2. Right? So if you use this, you will have, so I will rewrite this here. So you have exponential minus lambda, and you have exponential. So what I have said is 1/2 of lambda. Okay, I'm sorry. We do it again. So this is smaller than exponential minus lambda, exponential. So what I have is 2 lambda over 2 plus 2 lambda square over 2. Okay? So what you see is that these two terms here cancel, and there is just this term that remains. So this gives me this upper bound here. All right, so I have this upper bound, which is valid as long as, so this bound is valid when x is smaller in absolute value than 1/2. So I need to have lambda smaller than 1/4. So if I have here this quantity alpha j times s, which is smaller than 1/4, which is guaranteed when I have this inequality here, then what I obtain is that this expectation is smaller than this upper bound that is obtained by just this formula. All right, so now we have exponential minus lambda s, the product over j of these terms. And again, I will use the fact that the product of exponential is exponential of the sum. So I will have this product will become the sum over j here. So I will have the square norm of alpha, so the square Euclidean norm of alpha. So I have exponential minus st, which comes from here, and then I have twice the square norm of alpha times s2, which comes from here. All right, so this bond holds for any s which is smaller than this quantity. So now we want to make this bond as small as possible. So if you want to have this bond as small as possible, this is a simple computation. What you see is that you need to choose s of this size. Okay, so this s is the s which minimizes this quantity under this constraint. And now if you plug this value in this bound here, you end up with this upper bound. So this upper bound is an upper bound on this probability. So you end up with this upper bound, which is exactly the same as saying that the difference between my quadratic form of epsilon j and this expectation is upper bounded by this quantity where psi follows an exponential distribution with parameter 1. So we have shown this upper bound here, and now we need to move to this upper bound. So actually it is a very simple upper bound that we use. So we simply use the fact that the Euclidean norm is smaller than the L1 norm times the infinity norm, right? So if I use this upper bound and I just divide by 4 here and multiply by 2 here, by using the fact that 2ab is smaller than a2 plus b2, I obtain that this quantity is smaller than this one. Okay? So I can upper bound this quantity by this quantity. And now when I take the maximum between this quantity and this quantity, I see that this one is always the largest. So what we have is that this is always smaller than this. So this was the first technical result that we were needed, which is an upper bound on deviation of quadratic form of Gaussian random variable. So I remind you that what we want is to analyze the spectrum of some random variable, of random matrices, sorry. So I want to say something about the operator norm of some random matrices. So what is the operator norm of a random matrix? Well, you know that it is equal to this quantity. So this is the maximum of the norm of AU over all the U that are in the sphere. But it turns out that we will consider matrices that are symmetric. And when a matrix is symmetric, it is also given by this formula, which is the maximum over all the U on the sphere of the absolute value of the scalar product between AU and U. So this is a very simple result that you can check by yourself if you have not already seen it. What will you do? You just, so you have a matrix A which is symmetric, so you can diagonalize it, and we quickly see that the maximum of this quantity will be achieved for U, which corresponds to the eigenvector related to the eigenvalues which has the largest absolute value. And you know that the eigenvalue with the largest absolute value is exactly the operator norm of A when A is symmetric. So why do I mention this formula? Because actually this formula is more convenient because here you see that we have something which is linear in the matrix A, so it will be easier to analyze it than this term which is not linear. So it is nice. So as I tell you, so the matrix A will be random, and we have to consider this quantity. So you may imagine that for a given U, we'll be able to say something about this quantity. But what is tricky here is that then we will have to take the maximum over all the U that are in the sphere. So taking a maximum usually is not an issue because we just take a union bound. But here, what you see is that we have a maximum which is over all the sphere. So we cannot just take a basic union bound because otherwise we just have plus infinity. So what we'll do is to use the following discretization lemma that will replace this maximum of the sphere by a maximum over a finite set so that we'll be able to use a union bound. So let us prove this state and prove this discretization lemma. So what does this lemma says? So I give the reference from the lecture notes here. The lemma says the following. For any delta which is positive, there exists a set n delta, which is a subset of the sphere, which has a cardinality, so which has a cardinality which is finite, and we can even say that the cardinality is smaller than 1 plus 2 over delta to the d, where d is the dimension. And for this set, we'll have that for any matrix which is symmetric, the operator norm of the matrix can be upper bounded by 1 over 1 minus 2 delta times the maximum over this set of the absolute value of AU scalar U. So what you can see is that here we have the same quantity as we had in the definition of the operator norm of A, but the difference is that instead of taking the maximum over all the sphere, we take the maximum over a set which is finite. But there is a price to pay for this. Here we have a constant which is slightly larger than 1. Okay? So when delta is small, this constant will be small, but this set may have a cardinality which becomes larger. So we will use this lemma in the following because we'll be able to use some union bound over a set which is finite, so it will be very convenient. So let us start by proving this bound, and then we will move to the proof of the theorem. So the first thing that we do is to construct this set here, this specific set, and we'll do it as follows. So we consider the sphere in dimension D, and we'll first pick at random some point in this sphere. Then we'll pick another point that will be in the sphere, but at least delta away from my first point, etc. And then I will pick another point that will be in the sphere, but that will be delta away from all the points that I have already selected. And I will repeat this process until it is not possible to find any points anymore. And this will happen just because your sphere is compact, so you know that you can recover it with ball of radius delta, so you know that at some point you will not be able to find any other point. So you have a set which is finite, and by construction it has the following properties. So first, all the points are in the sphere because you have picked them in the sphere. And also, if you take 2 points in this set, they are delta away because each time you have been very careful to choose a point which is delta away from the others. And you have these additional properties that will be important, which is that now if I take any point which is in the sphere, I am able to find a point in my set n delta which is at least as close as delta from V. Okay, so you always find a point in L delta which is delta close to V. So why is it true? Well, just imagine that you cannot find such a V. So if you cannot find such a V, it means that you have a V, so there exists V in your sphere, such that for any U in L delta, you have U minus V, which is larger than delta. But you know that you have stopped because it was not possible to find such a V. So when you have constructed N delta, you have stopped when it was not possible to find such a V anymore. So by construction, you know that you cannot find a V such that this does not hold. Okay? So by construction, you know that for any V in the sphere, you have this property. All right, so it will be the two important properties that you will use. And now the first thing that we will do is to give an upper bound on the cardinality of the set N delta. So let me do a small picture. So what we have is that we have our sphere, and then we have picked some points which are all delta away from each other. So what you know is that if you look at the ball which have a radius delta over 2, you know that these balls are disjoint. Okay, so if you take the ball centered in this set N delta, the ball which have a radius delta over 2, by construction, you know that they are disjoint because all the points are all at least delta away one from the other. But at the same time, you know that this ball is included in the ball here, which has a radius 1 plus delta over 2. Okay, so all my small balls are included in this large ball. Okay, so the volume, the sum of the volume of all these small balls is smaller than the volume of this large ball. So this is exactly what we say here. We have a disjoint union of balls, which are all included in this large ball. And if we compare the volume, since these balls are disjoint, so this corresponds to the number of balls times the volume of this ball. So you know that the volume of this ball will be equal to the volume of the ball of the radius 1 multiplied by the radius to the d, so the radius is delta over 2. And here, what you will have is the same. You have the volume of the ball of radius 1 multiplied by the radius to the b, so you have 1 plus delta 2 to the b. These two volumes here cancel out, and you obtain an upper bound on the cardinality of n delta, which is this term divided by this term, which is exactly equal to this term. All right, so what we have proved so far is that we have a set which has a cardinality here, which is upper bounded by this quantity, and which satisfies these properties, which are, so this set is included in the sphere, and for any point in the sphere, you can find a point in your set which is at most delta away from your point. So now we'll use this in order to do some approximation of the operator norm. So I remind you that the operator norm for my symmetric matrix is given by the maximum over the sphere of the absolute value of the scalar product. And since the sphere is compact, the maximum is achieved at some u star. So if I code u star where the maximum is achieved, I have that the operator norm is given by this quantity, so for some u star which is in the sphere. But now I can use the fact that here I can find a u in my n delta which is at most delta away from u star. So if I use this u, I will have that I can use the following decomposition in order to upper bound the operator norm. So first, I will replace u star by u, and then I will just add these two terms in order to have a sum which is equal to u star scalar u star. So once I have done this, I can use the following upper bound. So first of all, I will use a triangular inequality, so I can upper bound by the sum of the absolute value. Okay. So here I have the absolute value of u. And now let me look at these terms. So what is the size of this term? So I remind you that here u belong to the sphere. So if I use Cauchy-Schwarz inequality, I will have that this is smaller than u star u times u, but the norm of u is equal to 1, so this is just the norm of u star minus u. And now, if I look at the norm of u star minus u, I can upper bound this by the operator norm of A times the norm of u star minus u. And you know that this is smaller than delta. So you end up by an upper bound, which is the operator norm of A times delta. So this is what you get for this term. And you can do exactly the same reasoning for this term. You will have the norm of this term times the norm of this term. So the norm of this term will be smaller than the operator norm of A, and the norm of this term is smaller than delta. So we'll have again that it is smaller than the operator norm of A times delta. So moving this term on the other side of the inequality, we end up with this bound, since this quantity here is smaller than, I remind you that u belongs to n delta, so it is smaller than the maximum over all the u and n delta of this absolute value. All right, so I hope that you have catch the main arguments. So where are we? Maybe you are a little bit lost, so let me come back to what we are doing. So what we want is to understand the spectrum of X transpose. Okay, and we want to prove this lemma, which tells us how these spectrums behave. And in order to prove this lemma, we have proved two preliminary results. The first one, which is the Hansen-White inequality that we will use, and the second one is this approximation result that will be very convenient in order to analyze the spectrum. So let us start by proving this part, so the low dimensional part of the lemma. The first thing that you will do is to denote by capital Z the matrix obtained by taking x small times sigma small minus 1/2. So this is a matrix which is n times kappa star, and it is simple computation, so it's not obvious for you. Just take a pen and check it. That this matrix will be IID, so we'll have entries that are IID standard Gaussian. All right, so you have a matrix which is n times kappa star with all the entries which are standard Gaussian and independent. And if you look at Z transpose Z, it is exactly equal to this quantity, which is the quantity where we want to understand how it behaves. Okay, this is the quantity that we have here. So we can write this as Z transpose Z, and we have seen that the entries of Z are IID standard Gaussian. So let us look at this quantity. So I look at the difference between this quantity and n times the identity in dimension k star. So as I said, I can rewrite this quantity as Z transpose Z. So I have the difference between the two. And now I use the fact that this is a symmetric matrix. So I can use my approximation upper bound for the operator norm, and I will use it with delta equal to 1/4. So if I use it with delta equal to 1/4, here I will have something that will be equal to 2, and here I will have 1 n to the 1/4. So I obtain this upper bound, where here my set lies in the sphere in dimension k star. So let us look at these terms. What do I have here? So maybe the simplest term is the second one. So if I look at this term, well, so I have the identity, so I just have n times the scalar product of u with u. So this is the norm of u star. And since u star, u belongs to the sphere, okay, I have u square, sorry, this is equal to 1. So here I will just have n. And for the second term, what do I have? So I have Z transpose Z times U, U. So I can write it as ZU, scalar ZU, by just taking my Z transpose and move it to the other side. So I have the square norm of Z in U for U, which belong to the sphere. So we have already discussed the distribution of this random vector, but we'll do it again. It turns out that this random vector will follow a standard Gaussian distribution in dimension n. So why is it true? So if I take a u which is in the sphere, and I look at the just coordinate of the u, zu, what I have is that, so this is just linear combination of the zgk. So first of all, I see that for different j, since I will look at different quantity, I will have some independence. And furthermore, you know that this is a Gaussian distribution with a variant which will be the square norm of u. I will have the sum over k of uk square. And this square norm is equal to 1 because I take a u which is in the sphere. So I have something which is IID n01. So this simply means that the vector zu follows the Gaussian distribution with covariance identity in Rn. So here I look at the square norm of this vector, so I can use Hansen-Wright inequality in order to analyze this. Okay, so I will look at Hansen-Wright inequality with alpha j equal to 1 or minus 1. So equal to 1 would be in order to have an upper bound on this minus n, and with -1, it will be in order, so set my -1, it will be in order to have an upper bound under this minus n, so it will be minus this plus n. So I will have an upper bound on the other side. So with my Hansen-White inequality, I have an upper bound on this, which is given by the following. So for each u, I can upper bound this by, so the L1 norm of my alpha over 4. So since all my alpha are equal to +1 or -1, this will correspond to n over 4. Plus, I remind you, 8 times the suit norm of alpha. So alpha are equal to 1 or +1 or -1. So we'll just have 1 here, times some exponential random variable. And this exponential random variable, of course, will depend on u. So I have this one, which corresponds to the upper bound, so with alpha equal to +1, +1, +1. And this one that will correspond to the lower bound on this quantity, because here I have some absolute value, so I need to have a bound upper and lower. And I will have another exponential random variable. So what you see is that you have an upper bound where you have a maximum of something that does not depend on you. And here you have the maximum of two random variables with exponential distribution of parameter 1. And this random variable depends on you. So now I will use a simple union bound. So if I look at this maximum, I can use a union bound in order to bound it. So we'll prove that 8 times the maximum over u of this quantity is larger than n over 8 with large probability. So for this, what we'll do just a union bound. So we'll take a union bound over all the u, and union bound over cu and psi prime u. So I will have twice the cardinality of 1 n 1/4 times the probability that my exponential random variable is larger than n over n 8 times 8. Okay, 8 times 8. So this is exponential n minus n over 64. And what can I say about this cardinality here? So this cardinality is smaller than, so I remind you that I have taken delta equal to 1/4. So this is exactly equal to 1 plus 8 to the d, which is 9 to the d. Okay, and here the dimension is k star, sorry. So since the dimension is k star, this is upper bounded by 9 over k star. So we have this can upper bound this maximum here by n over 8 with this probability. And now by using the fact that k star is small compared to n, we can go further and obtain this upper bound when we have that it is smaller than exponential n over 84. So this proves the first part of the theorem. Why does it prove this part? Simply because what we have shown is that with high probability, this is smaller than 8n over 8. Okay, so then I will multiply everything by 2. So if I multiply everything by 2, I will obtain that this is smaller than n over 2 plus n over 4, which is n, so 3n over 4, sorry. And this is exactly the bound that we had here. So now let us move to the second part of the bound. So this is quite standard. This is really what you have when you do a low dimensional regression. What is non-standard is this part. So this is this part which tells you that in the high dimensional space, you have a spectrum which is essentially flat around this value. So let us look at this high dimensional part. So we'll do exactly the same as before. We will renormalize the x by sigma minus 1/2, but we simply restrict to the high-dimensional part. So we can do exactly the same reasoning. And if you do the same reasoning, so what you have is that x transpose in this high-dimensional part, so it is z sigma z transpose in the high-dimensional part. And of course, so what is the expectation of this? Since z are standard Gaussian, it will simply be the trace of this matrix times the identity. So we take the look at the difference between the two, and by using again my Hanson-Wright inequalities, you obtain that. So I use Hanson-Wright inequalities, but with some weights that depend on lambda, right? You will obtain the fact that this can be upper bounded by something like this, where I have the sum of the eigenvalues divided by 4, which correspond to the A1 norm of alpha over 4, plus 8 times, so the eigenvalue lambda k star plus 1, which corresponds to the largest coefficient alpha, so the alpha are equal to the lambda j, so for j larger than k star, so this is this value which is the largest, times this random variable which have an exponential one distribution. So again, we can use the same kind of reasoning in order to do the upper bound. So we do a union bound. And by using the very definition of K star, we have that this quantity is smaller than, okay, so this quantity here is smaller than rho over n times the trace of sigma in the high-dimensional space. Okay, we know that it is smaller. This is really by the definition of K star. So since we have this inequality, we can upper bound this probability by this probability. And by just using a union bound as before, we'll have twice the cardinality of n to the 1/4. So in this case, n to the 1/4 is included in the sphere of dimension 1. So I have the cardinality which is upper bounded by 9 to the n times the exponential minus this quantity, so the exponential minus n64 times rho. And by using the fact that 1 over rho is equal to 1 over 42, we end up with this upper bound for this probability. All right, so for the second term, what we have done is we have just applied here Hanson-Wright inequality with the alpha j corresponding to the lambda j for j larger than k star. And then, just as before, we have used this upper bound with delta equal to the 1/4 in order to get this upper bound on the operator norm. And then by using just a union bound on the very definition of K star, so I remind you that the definition of K star, so this is the smallest k for which we have this inequality here. So by using this inequality for k equal to K star, we add here that this probability is smaller than this one, and with a simple union bound, we get this inequality. All right, so what have we done so far? So what I remind you what we are doing. What we are doing is to try to understand this variance term, and for this to try to understand this matrix. As we have discussed, it is easier to understand this matrix here than this matrix, and since they have the same non-zero spectrum, I will have all the information that I did by looking at this matrix. And what we have seen here with this result is that essentially this matrix behaves like n times the covariance on the low dimensional part. This is what you get when you have a low dimension regression, times something which behaves like some lambda star, which is the sum of the remaining eigenvalues, times some random projector of dimension n minus k. Okay, so this will be a random projector on a space of dimension n minus k star. And now we'll use this approximation. Okay, so we use the precise result that we have shown, but essentially we'll use this approximation in order to understand how is the variance. But maybe it is wise to have a small pause before moving to the following. So let us now turn to the main result of this series of lecture. So this is a result of Bartlett et al. From 3 years ago, and it gives us an upper bound on the variance of the estimator based on this result that we have seen before. So what it tells us is that if we define this k star, which corresponds to the low dimensional part of the signal with this formula, if k star is small enough, so if k star is smaller than n times some small constant, we have that the variance is upper bounded essentially by, so we have sigma 2, and you will have the sum of two terms. You have one term which is k star over n, which is really the term that we are used to see when we do low dimensional regression, dimension divided by n. So this corresponds to the low dimensional part. And we have an additional term, which is here, which corresponds to the high dimensional part, and this term is given by n times the sum of the eigenvalue to the square divided by the sum of the remaining eigenvalue to the square. And this term will typically be small in high dimension, so you can see some high dimensional regularization effect. So we'll discuss a bit more this upper bound later. First, what we'll do is to prove this upper bound. So I remind you, so the variance is given by this formula. So sigma 2 is here, so essentially what we need is to understand this Frobenius scalar product. So what we want to do is to disentangle the low rank part from the high dimensional part. And this is something that we can do simply thanks to the following lemma. So what we will see is that this term can be upper bounded by the same term for the low dimensional part plus the same term for the high dimensional part. So how do we get this? So I remind you that what is nice when we look at X transpose is that we can separate the low dimensional part from the high dimensional part. So this is not something that you can do with X transpose X, but this is something that you can do with X transpose. So since here we have X transpose X, what we will do is to make appear X transpose. How can we do this? Well, actually, you can readily check that we have this inequality, that X transpose, and you take the Moore inverse pseudo inverse, is equal to X transpose, X transpose, where you take twice the Moore inverse pseudo inverse, times X. Right? So this simply amounts to take the singular value and takes, instead of taking 1 over the singular value, you take 1 over the singular value to the square. So how it is not obvious for you, this formula, just look at the SVD of this matrix and you will recover the SVD of this matrix. Okay, so I repeat that here, what I do, I take the SVD of X transpose, and what I will do is to take 1 over the singular value to the square. Okay, so if I take, I can take a diagonalization. If I look at x transpose 2 plus, this is just the sum over k of 1 over lambda k to the square uk transpose. Okay, so in this case, you don't have to care about singular vectors because you have something which is symmetric. All right, so I will start from this inequality, and now I can use the fact that here I can decompose x transpose by splitting the low rank part on the high dimensional part. So I will use this inequality. So here, as I said, so I have this equality here. And what I will do when I use this equality that we have seen, I will move this on the other side, okay, of the scalar product. So I have that x plus x, x transpose x plus sigma is equal to x transpose 2 plus scalar x sigma x transpose. And now if I look at this part, again, I will have a decomposition like this. So I will have the low dimensional part and the high dimensional part. I could have set this in red to keep my usual colors. All right, so so this is nice. Here I can separate the low dimensional and the high dimensional part. But here I have a Moore-Penrose pseudo-inverse, so this is not the sum of the two. Okay, so I tell you, okay, it is nice. I can separate here low dimensional part and high dimensional part, but it turns out that I have the Moore-Penrose pseudo-inverse, so it will not work directly. But we will use a very simple upper bound. So since we have this inequality here, okay, this is positive semi-definite, this is positive semi-definite, you have that this matrix dominates this matrix in terms of positive semi-definite matrix. Okay, so you have this dominance here, and you have the same for the high dimensional part. So since you have this dominance, well, what does it mean for the inverse? So if you take the Moore-Penrose pseudo-inverse, you will not have, okay, if you take just the Moore-Penrose pseudo-inverse, you will not have this. This is not true everywhere, but this will be true on the range of this matrix. So if you take the Moore-Penrose pseudo-inverse, you will have that, so here we'll take the double Moore-Penrose pseudo-inverse, you will have that this matrix will dominate this matrix on the range of the low dimensional part of X. All right, so you can invert like this, but not everywhere, only on the range of the low dimensional. And you have the same for these two terms, so you will have the same, and it will be on the range of the high dimensional part. So now let us come back to this quantity here. So first we look at the scalar product with the low dimensional part. So in this case, you see that this matrix lives on the range. Okay, the range of this matrix is the same as the range of the low dimensional part of X. So I can use the fact that this matrix here is dominated by this matrix. Okay, so by using this, I have this inequality. Okay, where I have replaced this by this just by using this upper bound that holds on the range of this low dimensional part of X. And you can do exactly the same reasoning for the high dimensional part. Okay, so by using this upper bound for the high dimensional part, you obtain this upper bound. And now what we have is that the term here that we want to analyze for the variance term is upper bounded by these two terms where you have disentangle the low dimensional part from the high dimensional part. So in order to get this upper bound, what we need is to analyze this term and this term apart. And we start with the low dimensional part. All right, so when you are in the low dimensional part, so I remind you that here you have a matrix which is k star times k star, and k star is small compared to n. So in particular, it is smaller than n. Remind you, it is smaller than n over 600. So it turns out that this matrix is full rank. So actually, your Moore-Penrose pseudo-inverse is just the classical inverse in this case. And since it is the classical inverse in this case, you can rewrite this as, so you take sigma 1/2, sorry, sigma 1/2 x transpose x inverse, sigma 1/2 scalar the identity. Okay, so you have this equality here, and now you can move the sigma minus alpha 1/2 inside the -1. So you move it on both sides inside. Okay, this is something that you can do because you have the true inverse, but of course you have to inverse. So instead of having 1/2, you will have -1/2. Right? So if I rewrite what we had here, so we had sigma 1/2 x what I will do is to move this guy and this guy inside, and this is why I obtain this formula here. And here I plainly use the fact that the Moore-Penrose inverse is exactly the usual inverse. All right, so what you see is that this term is nothing but the trace of this matrix, the inverse of this matrix. So we have analyzed this matrix. Here we take the inverse, and this is the trace of this inverse. So what we have seen is that if you look at this matrix that shows up, this matrix, if you look at the eigenvalue, they are larger than n minus 3/4 of n. Okay? So the eigenvalues of this matrix are at least equal to n over 4. So since the eigenvalue of this matrix is at least n over 4, if you take -1, it means that it will be smaller than 4 over n. Okay? So the eigenvalue of this matrix are smaller than 4 over n. So now if I take the trace of this matrix, this is a matrix which is k star by k star. So the trace will be at most this time k star, which is the number of eigenvalues that I have. So I end up that this trace here is at most 4 times k star over n. So I have that this first term is upper bounded by 4 k star over n, of course, with high probability. So here we have shown that the first term here is smaller than 4 times sigma 2 k star over n. And this is something that we are used to see if you do some classical low dimensional regression. But here this also happens in our high dimensional setting. in the space where the signal is large. So now, let us move to the high-dimensional term, which is the second term here in my upper bound. So again, we will use the lemma on the spectrum. So let us look at this lemma. What does it say? It says that this spectrum behaves essentially as this quantity, in the sense that it is always larger than 1/4 of this quantity for the same reason, because it is larger than this quantity minus this quantity. And it is also smaller than 1 plus 3/4 times this quantity. Okay, so these eigenvalues up to a constant, they are of this size. So let us use this upper bound. So what we have seen, so just discussed, is this inequality. So the spectrum is between 1/4 of the trace and twice the trace. So what we can do is to lower bound this matrix by, this matrix by this times the identity. Okay, so if I look at the high-dimensional part of X transpose X, it is larger than the trace over 4 times the identity ENM. All right, so now if I take twice the Moore-Penrose pseudo-inverse, I will end up with the fact that this matrix will be smaller. So again, emphasize that it is in terms of domination of positive semi-definite matrix. So it will be smaller than 1/4 the trace of sigma to the square times the identity. And by using this bound here, so I will use this bound here. So first of all, I rewrite this scalar product in this way. So this is exactly what we had done here in this inequality here. So I rewrite this bound in this way. And by using that this matrix is dominated by 4 over the trace divided to the 2, times the identity, I end up by the fact that this scalar product is upper bounded by 4 over the trace to the square times the trace of this matrix. Okay, so here I use the fact that the spectrum is always larger than this. So I have an upper bound, but still I have to understand what is the trace of this matrix. So let us analyze this trace. So I will do as before. I will use the fact that I can write X large sigma minus I half as some Z, where the Z is a matrix with a standard Gaussian random variable. Okay, so the entries of Z are IED standard Gaussian. So by replacing X by Z, I get this formula here. So maybe I will zoom in a little bit. So I obtain this formula here. And I can expand this formula. So what is this formula? So I look at the trace of this matrix. So this is simply the sum of the diagonal term of this matrix. And now I can write what is this matrix. So I remind you that here I have a diagonal matrix. So what is this matrix? This is a diagonal matrix where I have the eigenvalues larger than k star to the square. So to the square is because I have a square. Yeah. All right. So what will be this entry? It will be simply the sum over j of the zij to the square times this eigenvalue to the square. So you recognize again, so this is the entry zij are IID standard Gaussian. So you recognize that we again have a quadratic form of standard Gaussian random variable with some coefficients which are given by this. So we will use Hanson-Wright inequality. Okay, so we will use this Hanson-Wright inequality here. And by using this Hanson-Wright inequality, I get the upper bound. Okay, so this corresponds to the L1 norm of the coefficient. So this corresponds to the sum of this coefficient. So I have the sum over I and the sum over j. And since you see that this does not depend on I will have n times the sum over j of this quantity. So this is why I have this term. And then I will have this additional term where I have the maximum of the coefficient. So the maximum is this term. And I will have 8 times some exponential random variable. And so this corresponds here to the fluctuation. But of course, this also has a mean, which is non-zero. And what is the mean of this? Well, this is the expectation of this quantity. So taking the expectation, this expectation is this is equal to 1. This is exactly equal to this quantity. So the expectation is equal to this term. So what we have is that this term is upper bounded by its expectation, which is here, plus the fluctuation, which is controlled by Hanson-Wright inequality, which is given by this term. And this, of course, holds with some random variables here. So we want to have a high probability bound. So this will be smaller than n over 32 with this probability. So by using this, by using the fact that probability that psi is larger than n over 32, this is smaller than exponential minus n over 32, we can upper bound this term by this term. So we end up by having here a bound which is like this. Okay, so this term corresponds to this term, and this term corresponds to this term. All right, so here I will just use a very crude bound. I will upper bound this by the sum. So I upper bound lambda k star plus 1 to the square by the sum over all the j larger than k star of the lambda j square. So it's quite crude. So at the end, I obtain that this term is upper bounded by 6 over 4 nth times the sum of the lambda j square. So putting pieces together, what I obtain is that this bound, this term here, is upper bounded by this term times this term. So this gives me this upper bound, and this upper bound is exactly the one that we get here. All right, so just a small recap in order to finish this lecture, which is a bit more technical than the others. So we have proved that the variance is upper bounded by this term, and actually we can prove a lower bound, which is of the same order of magnitude up to some constant. So actually this is really the order of magnitude of the variance. Okay, so this upper bound is almost an equality. And again, we have this low dimensional part, which is very classical when you do low dimensional regression. and we have this high-dimensional part, which corresponds to regularization from the high-dimensional input. And this corresponds to the fact that in this high-dimensional input, we essentially predict by zero. So we essentially have something which has no variance. So maybe it is interesting to try to see if we can recover the non-rigorous computations that we have done in the last video. So we have been considering two cases, the isotropic case and the spike model. So let us first look at the isotropic case, when sigma is equal to the identity. So if sigma is equal to identity and p is large compared to n, well, you will have here, so this is equal to 1, this is equal to 1, okay? So here you have n smaller than rho p minus k. And you see that if n is very small compared to n, well, this will hold. You will have this inequality that will hold for any k. So k star will be equal to 0. Okay, so if you have k star equal to 0 in this term, so this means that this disappears, and you will just have this term. But what is this term? So since you have the identity, here you have 1, here you have 1. Okay, so here you will have p, and here you will have p to the square. Okay, so you will end up with something that will be sigma 2, so this sigma 2, n times p, okay, n times p, and p to the square. So you end up with sigma n over p, and we exactly recover our guess from the previous video. So let us look now to the spike model. So if you look at the spike model, so we have the low dimensional part, and we have a high dimensional part with a small sigma, so alpha is small. And we assume that k is small compared to n compared to rho. So again, what we will have is that if alpha is small and k is small compared to n, here kappa star will be nothing but exactly the k that shows up here. So we have this formula with k star equal to k. So let us replace in this formula with k star equal to k. And what will be the lambda j? The lambda j, since it is for j larger than k star, the lambda j, so I will have lambda j equal to alpha. This corresponds to this eigenvalue here. So the first term will be k over n. And for the second term, so I have n here. And then I have p minus k times alpha to the square. So p minus k times alpha to the square. And here I have p minus k times alpha, p minus k times alpha, and everything is to the square. So by using the fact that k is very small compared to n, so I can forget about the k here, and you have the p that will cancel out, you have the alpha that will cancel out, so you end up with this formula, sigma 2 k over n plus n over p, and this is exactly the guess that we had from our informal computation. So we recover the result that we have guessed the last time, and recover the fact that we have this low dimensional part and this high dimensional regularization. So far I have not talked about the bias. So I will give you a few words about the bias. We will not do the analysis. What we can show is that if you look at the bias term, again, you will have two terms, one from the low dimensional part and one from the high dimensional part. So if you look for the low dimensional part, you will have this upper bound for the bias. And actually, this is something that tells you that you will have a bias which should be small for this low dimensional part. This should be small. So you will have something, so it is multiplied by this, but you will have something that will be small thanks to this term. So at least if n is large compared to k star. So you can expect to have a small bias on the low dimensional part. But if you look at the high dimensional part, what you will have is that you have almost a full bias. You almost predict with 0, so you almost have the bias that you get when you predict with 0. So potentially you can have a bias here which is very large. Okay, so we have the opposite phenomenon that we had. So we have something which is nice in the low dimensional part, but we have a large bias for the high dimensional part, which is a counterpart of the fact of having a small variance for the high dimensional part. And maybe something interesting is to note that this bias is almost the bias of a ridge regression for the low dimensional part by using regularization penalty, so regularization parameter, in your ridge penalty, which is given by this formula, where you will regularize by the sum of the remaining eigenvalue divided by n. So what is the take-home message for today? So what we have seen is that in the interpolation regime, the gradient descent least square estimator has a behavior where we can distinguish what happens for the low dimensional part and the high dimensional part. So for the low dimensional part, this is something that you can estimate well, because you will have a small bias and a variance that will be small also, because it is like k over n, and k is small compared to n. But for the high dimensional part, you will estimate it essentially by 0. So you will have a large bias from here, but you will have a small variance, as we have seen before. So as you can see, this is quite counterintuitive from what we are used to think. The high dimensional part has a large bias, but a small variance. And this is a regularization effect, which is implied by the high dimension. Essentially, you will predict by 0 because a new input will be not correlated with your input from the learning dataset. So that's all for today. And in the last short video, I will briefly discuss Benign overparametrization.